Good day, esteemed researchers and viewers worldwide. We're excited to present our paper, MiniGPT-3D, efficiently aligning 3D point clouds with large language models using 2D priors, authored by Yuan Tang, Xu Han, Xianji Li, Chao Yu, Yishui Hao, Long Hu, and Min Chen. This research addresses the challenge of understanding 3D point clouds using 2D language learning models. Stay tuned as we delve into our innovative 4-stage training process that efficiently transfers knowledge from 2D to 3D space, offering new insights into 3D comprehension. Begin our frame. Frame title our approach. Begin itemize. Item stage 2 begin itemize. Item we fine tune 4 parts. The point cloud projection layer, the Q former, the modality projector, and the LLM. Item we use the same dataset from the first stage to train 47.4M parameters. Item this stage helps us transfer the vision language knowledge domain to 3D space and itemize. Item stage 3 begin itemize. Item we further fine tune the modules trained in the second stage. Item we use a more challenging dataset to empower MiniGPT-3D with the ability to comprehend and respond to complex instructions and itemize. Item training stages begin itemize. Item our training process includes 4 stages, each focusing on a distinct task. Item this process enhances the nascent 3D LLM's comprehension and transfers the priors of 2D LLM to point cloud modality and itemize, end frame, begin our frame. Frame title key highlights, begin itemize, item key insights and approach. Begin itemize. Item our novel 4-stage training process is designed to gradually transfer the priors of 2D LLM to point cloud modality, enhancing the comprehension of nascent 3D LLMs. Item in the first stage, we focus on bridging the knowledge gap between the 3D point cloud encoder and 2D LLM modules. This is achieved by training the point cloud projection layer while keeping other modules frozen. Item, the second stage, is dedicated to transferring the vision language knowledge domain to 3D space. We fine-tune 4 parts: the point cloud projection layer, the Q former, the modality projector, and the LLM. This allows the 2D LLM modules to gain comprehension of 3D point clouds. End itemize, end frame, In this slide, we're highlighting the key contributions of our work. First, we introduce MiniGPT-3D, a model that is not only efficient but also powerful in the realm of 3D language models. This model is unique in its approach as it aligns 3D points with large language models using 2D priors. This innovative alignment strategy is a significant step forward in the field. Moreover, our model achieves multiple state-of-the-art results, and it does so with impressive efficiency. It requires only 26.8 hours of training on a single RTX 3090. This is a testament to the model's efficiency and the potential it holds for future research and applications. In summary, MiniGPT-3D is a game-changer, offering a new, efficient way to connect 3D point clouds with large language models. Begin our frame. Frame title key highlights. Begin itemize. Item main idea and method. Begin itemize. Item our approach leverages the power of 2D LLMs to bridge the gap between language learning models and 3D data. This is a significant step towards creating a 3D language knowledge domain. Item, we achieve this alignment through a meticulous fine-tuning process involving 4 key components: the point cloud projection layer, the Q former, the modality projector, and the LLM. This process allows us to transfer the knowledge from 2D to 3D, enhancing the comprehension of 3D point clouds. End itemize, end frame, begin our frame. Frame title key highlights. Begin itemize. Item key results. Begin itemize. Item we've trained a whopping 47.4 million parameters using the same dataset from the first stage, ensuring a smooth transition of knowledge from 2D to 3D. Item, our MiniGPT-3D has achieved new state-of-the-art performance on generative 3D object classification and object captioning tasks, showcasing its potential. End itemize. Item author's message. Begin itemize. Item, we've demonstrated the feasibility and efficiency of transferring vision language knowledge from 2D to 3D space, opening up new avenues in 3D language comprehension. Item, our method efficiently aligns 3D point clouds with language learning models, LLMs, leveraging the power of 2D LLM knowledge, which sets a new benchmark in the field. End itemize, end frame, begin our frame. Frame title a training stages overview, begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC task underscore execution extracted underscore paper underscore data, 2405.01413v1 figures, 2405.01413v1 figure 3:1.png, caption Atinia, the 4 stages of training MiniGPT-3D, end a figure, begin itemize, item training process, begin itemize, item 4 stages, each with a unique focus, item stage 2, transfer of vision language knowledge to 3D space, item stage 3, fine-tuning for better 3D language comprehension, end itemize, end frame. In our training process, we have 4 distinct stages, each with a unique focus. In stage 2, we aim to transfer the vision language knowledge domain to 3D space. This involves fine-tuning 4 parts: the point cloud projection layer, the Q-former, the modality projector, and the LLM. The goal is to enable the 2D LLM modules to understand 3D point clouds and gradually transfer the powerful priors to the 3D language knowledge domain. Moving on to stage 3, we further fine-tune the modules trained in stage 2. We use a more challenging dataset, which includes detailed caption, point cloud pairs, and conversations. This empowers MiniGPT-3D with the ability to comprehend and respond to complex instructions, enhancing its 3D language knowledge. Begin a frame. Frame title our training approach. Begin a figure. Centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC task underscore execution extracted underscore paper underscore data, 2405.01413v1 figures, 2405.01413v1 figure 3:1.png, caption Atinia, the 4 stages of our training process for MiniGPT-3D, end a figure, begin itemize, item our training stages, begin itemize, item we employ a 4-stage training process to enhance 3D LLM's comprehension. Item stage 2 focuses on transferring vision language knowledge to 3D space. Fine-tuning 4 key parts. Item stage 3 further fine-tunes the modules, using a challenging dataset for better 3D language knowledge. End itemize, end a frame, begin a frame. Frame title a training stages of MiniGPT-3D. Begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC task underscore execution extracted underscore paper underscore data, 2405.01413v1 figures, 2405.01413v1 figure 3:2.png, caption Atinia, 4 stages of training process for MiniGPT-3D, end a figure, begin itemize, item stage 1, bridging the knowledge gap, begin itemize, item focuses on connecting the 3D point cloud encoder and 2D LLM modules. Item trains the point cloud projection layer using 660K caption point cloud pairs, end itemize, item stage 3, enhancing 3D language knowledge, begin itemize, item fine-tunes the modules trained in the 2nd stage, item utilizes a challenging dataset to comprehend and respond to complex instructions, end itemize, end a frame, In this slide, we delve into our proposed solution to the challenge of efficiently connecting large language models, or LLMs, with 3D data. We introduce the concept of using 2D vision language models, known as 2D LLMs, as a strong prior. This approach allows us to leverage the existing alignment between 2D images and language, reducing the cost of aligning 3D point clouds with LLMs. Building on this idea, we present MiniGPT-3D, an efficient 3D point cloud language model that utilizes 2D LLMs as priors. The figure you see here illustrates the training framework and strategy of MiniGPT-3D. This model not only achieves state-of-the-art results, but also significantly reduces the training time and resources required, making it a promising solution for the efficient integration of 3D data with LLMs. Let's delve deeper into the training framework and strategy of MiniGPT-3D. As you can see in the figure, our model is trained in 4 stages, each with a specific focus. The first 2 stages use brief captions as training data, while the more complex detailed captions and conversations are introduced in stages 3 and IV. This progressive approach allows the model to gradually build its understanding of 3D language knowledge. Now, let's talk about the achievements of MiniGPT-3D. It has achieved multiple state-of-the-art results, demonstrating its effectiveness. Moreover, it's efficient. The entire training process requires only 27 hours on a single RTX 3090 GPU. This efficiency makes MiniGPT-3D a practical solution for real-world applications. In the next slides, we will discuss more about the model's architecture and the specific training details. Stay tuned. Let's delve into the training strategy of MiniGPT-3D. Our approach is characterized by an efficient four-stage training strategy, which is designed to gradually learn unified visual textual representations. This strategy is crucial in transferring the priors of 2D LLM to point cloud modality and enhancing the nascent 3D LLM's comprehension. As you can see in the figure, each stage focuses on a distinct task, allowing the model to progressively build its capabilities. In the third stage, for instance, we fine-tune the modules trained in the second stage using a more challenging dataset. This empowers MiniGPT-3D to comprehend and respond to complex instructions, thereby improving its 3D language knowledge. This strategic approach ensures a robust and comprehensive training process for our model. Let's delve deeper into the mixture of query experts, or MQE, a key component of our MiniGPT-3D training framework. As you can see in the figure, MQE is a unique system that comprises multiple query experts and an expert router. This setup allows for the adaptive aggregation of features, enhancing the model's perception and cognition. What's remarkable is that this is achieved with only 0.4 million parameters, demonstrating the efficiency of our approach. This innovative feature of MiniGPT-3D allows it to adapt and respond to complex instructions, making it a powerful tool in 3D language knowledge comprehension. On this slide, we delve into the training framework and strategy of MiniGPT-3D, as depicted in the figure. Our approach is centered around parameter-efficient fine-tuning technologies. We've leveraged the power of LoRa and norm fine-tuning, which has been instrumental in reducing the model's training overhead. This fine-tuning process is crucial in our quest to transfer the vision language knowledge domain to 3D space, thereby establishing the 3D language knowledge domain. The goal is to empower MiniGPT-3D with the ability to comprehend and respond to complex instructions in a 3D environment. This is a significant step forward in our training stages, and it sets the stage for the next phase of our research. Begin a frame title the challenge and our solution, begin itemize, item the challenge, begin itemize, item existing 3D LLMs directly align point cloud encoders with LLMs, requiring substantial resources for alignment. Item training 3D LLMs is resource-intensive and challenging. End itemize, item our solution. MiniGPT-3D, begin itemize, item an efficient 3D LLM that connects 3D point clouds and LLMs using 2D LLMs as priors. Item achieves state-of-the-art results with only 27 hours of training on a single RTX 3090 GPU. Item utilizes an efficient four-stage training strategy, gradually transferring the knowledge from 2D LLMs to 3D. Item introduces the mixture of query experts, MQE, for adaptive feature aggregation. End itemize, end frame, begin a frame. Frame title our solution. MiniGPT-3D, begin itemize, item we introduce MiniGPT-3D, a novel and efficient 3D LLM that leverages 2D LLMs as priors to align 3D point clouds with LLMs. Item our model achieves multiple state-of-the-art results with only 27 hours of training on a single RTX 3090 GPU. Item we propose a four-stage training strategy that gradually transfers knowledge from 2D LLMs to 3D, requiring only 47.8 learnable parameters. Item we design the mixture of query experts to aggregate features from different experts with only 0.4 parameters. End itemize, end frame, begin a frame. Frame title training stages of MiniGPT-3D, begin itemize, item four-stage training strategy, begin itemize, item gradual transfer of knowledge from 2D LLMs to 3D, item only 47.8 learnable parameters required. End itemize, item stage 2. Establishing the 3D language knowledge domain, begin itemize, item fine, tuning 4 parts, point cloud projection layer, Q-former, modality projector, and the LLM. Item utilizes the 3D to D bridge from the first stage. Item trains 47.4M parameters. End itemize. Item mixture of query experts, MQE, begin itemize. Item comprises multiple query experts and an expert router. Item aggregates 3D features from multiple perspectives into the semantic space of 2D LLM. Item only 0.4M parameters. End itemize. End itemize. End frame, begin frame. Frame title, training details and results. Begin itemize. Item training settings. Begin itemize. Item utilized point. Text instruction dataset with 660K brief captions and 70K detailed captions in conversations. Item employed Atom W optimizer and a cosine decay learning rate schedule. End itemize. Item model parameter. Begin itemize. Item total of 2.95B model parameters. Trained 47.8M parameters on a single RTX 3090 GPU. Item training took 27 hours. End itemize. Item training loss. Begin itemize. Item observed a steady decrease in loss across the 4 training stages. Item temporary increase in loss during stage 3 and IV due to introduction of more challenging tasks and training of MQE from scratch. End itemize. End itemize. End frame, begin frame. Frame title of the 4-stage training strategy of MiniGPT-3D. Begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data. 2405.01413v1, figures, 2405.01413v1 figure 3:1.png, captiona, tinea, the 4-stage training strategy of MiniGPT-3D. The figure illustrates the process of training the point cloud projection layer, MLP, the Q-former, the modality projector, and the LLM backbone, and how these components are fine-tuned to enhance 3D comprehension. End figure, begin itemize. Item, the first stage of training focuses on bridging the knowledge gap between the 3D point cloud encoder and 2D LLM modules. This is achieved by training the point cloud projection layer, with other modules remaining frozen. Item, in the second stage, the aim is to transfer the vision language knowledge domain to 3D space, thereby establishing the 3D language knowledge domain. This is done by fine-tuning 4 parts: the point cloud projection layer, the Q-former, the modality projector, and the LLM. Item, the third stage, involves further fine-tuning of the modules trained in the second stage. A more challenging dataset is used to empower MiniGPT-3D with the capabilities to comprehend and respond to complex instructions. End itemize. End frame, begin frame. Frame title of the 4-stage training strategy, begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data, 2405.01413v1 figures, 2405.01413v1 figure 3:2.png, captiona, tinea, the progression of the training stages, highlighting the fine-tuning of the modules and the use of a challenging dataset. End figure, begin itemize. Item stage 2. Fine-tuning 4 key components to establish the 3D language knowledge domain. Begin itemize. Item, the point cloud projection layer, the Q-former, the modality projector, and the LLM are fine-tuned. Item, the same dataset from stage 1 is used to train 47.4M parameters. End itemize. Item stage 3. Further fine-tuning and use of a more challenging dataset. Begin itemize. Item, detailed caption, point cloud pairs and conversations are used to enhance MiniGPT-3D's comprehension and response to complex instructions. End itemize. End frame, begin frame. Frame title of the 4-stage training strategy, begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data, 2405.01413v1, figures, 2405.01413v1 figure 3:1.png, captiona, tinea, the 4-stage training strategy of MiniGPT-3D. The figure illustrates the process of training the point cloud projection layer, MLP, the Q-former, the modality projector, and the LLM backbone, and how these components are fine-tuned to enhance 3D comprehension. End of figure, begin itemize, item the journey. We're leveraging pre-trained 2D LLMs to enhance their understanding of 3D point clouds. Item the strategy. Our 4-stage training strategy, as shown in the figure, involves fine-tuning the MLP, Q-former, modality projector, and LLM to boost 3D comprehension. Item the benefit. This approach not only connects LLMs with 3D data, but also reduces the cost of vision-language alignment. End itemize, end of frame, .. On this slide, we delve into the technical details of our proposed research. We've developed a 4-stage training strategy to gradually transfer the knowledge from 2D language learning models, or 2D LLMs, to 3D. In the second stage, we focus on transferring the vision-language knowledge domain to 3D space. This is achieved by fine-tuning 4 key components: the point cloud projection layer, also known as MLP, the Q-former, the modality projector, and the LLM. As you can see in the figure, these components are meticulously fine-tuned to enhance 3D comprehension. This process is crucial in establishing a 3D language knowledge domain, which is a significant step forward in our research. In the next stages, we continue to fine-tune these modules and use more challenging datasets to further enhance the 3D comprehension capabilities of our model. Stay tuned for more details on these stages. Begin a frame. Frame title of the 4-stage training strategy, begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, SRC, task underscore execution extracted underscore paper underscore data, 2405.01413v1, figures, 2405.01413v1 figure 3:1.png, captiona, tinea, the 4-stage training strategy of MiniGPT-3D. The figure illustrates the process of training the point cloud projection layer, MLP, the Q-former, the modality projector, and the LLM backbone, and how these components are fine-tuned to enhance 3D comprehension. End of figure, begin itemize, item the 4-stage training strategy. This strategy is designed to gradually transfer the priors of 2D LLM to point cloud modality, enhancing the nascent 3D LLM's comprehension. Item stage 2. In this stage, the objective is to transfer the vision language knowledge domain to 3D space, establishing the 3D language knowledge domain. 4 parts are fine-tuned: the point cloud projection layer, MLP, the Q-former, the modality projector, and the LLM. Item stage 3. To gain better 3D language knowledge, the modules trained in the second stage are further fine-tuned using a more challenging dataset. This empowers MiniGPT-3D with the capabilities to comprehend and respond to complex instructions. End itemize, end of frame, .. In this slide, we delve into the technical details of our research. As you can see in the figure, our 4-stage training strategy for MiniGPT-3D is illustrated. The key components of our method include the point cloud projection layer, the Q-former, the modality projector, and the LLM. These components are meticulously fine-tuned. The objective: to gain a comprehensive understanding of 3D point clouds. This fine-tuning process is crucial as it allows us to transfer powerful priors into the 3D language knowledge domain. In essence, we're not just teaching the system to see in 3D, but also to understand and interpret this 3D information in the context of language. This is a significant step forward in the field of 3D comprehension and language understanding. In this slide, we delve deeper into the technical aspects of our research. The figure you see here illustrates our 4-stage training strategy for MiniGPT-3D. It shows how we train and fine-tune key components such as the point cloud projection layer, the Q-former, the modality projector, and the LLM backbone. These components are crucial in enhancing the 3D comprehension of our model. Now, let's talk about our experiment design. We use the same dataset from the first stage to train 47.4 million parameters. This approach not only demonstrates the efficiency of our method, but also minimizes the impact of the 3D-2D bridge. For those interested in the specifics of our training process, we have outlined it in Table 1. In the next slides, we will further discuss the results and implications of our research. Stay tuned. Let's delve deeper into the technical aspects of our research. We've developed MiniGPT-3D, a highly efficient 3D language learning model, or 3D LLM. This model ingeniously bridges the gap between 3D point clouds and language learning models, leveraging the power of 2D LLMs as a foundation. Now, you might be wondering about the training loss for MiniGPT-3D. Well, we've got that covered too. The training loss is meticulously calculated and optimized to ensure the best performance of our model. As you can see in the figure, our 4-stage training strategy is illustrated. It shows how we train the point cloud projection layer, the Q-former, the modality projector, and the LLM backbone. Each of these components is fine-tuned to enhance 3D comprehension, making MiniGPT-3D a robust and versatile model. In essence, our research proposes a novel approach to 3D language learning, pushing the boundaries of what's possible in this exciting field. Begin at frame title at proposed research and technical details. Begin itemize. Our training process is divided into 4 stages, each focusing on a unique task. In stage 2, we fine-tune 4 parts: the point cloud projection layer, the Q-former, the modality projector, and the LLM. This helps us transfer the vision language knowledge domain to 3D space. We use the same dataset from the first stage to train 47.4M parameters, minimizing the impact of the 3D-2D bridge. In stage 3, we further fine-tune the modules and use a more challenging dataset. This empowers MiniGPT-3D to comprehend and respond to complex instructions. Itemize. Frame. Let's now delve into the technical results of our research. On the left, you can see a visual representation of the 3D question answering results of MiniGPT-3D. This figure illustrates the effectiveness of our model in comprehending and responding to complex instructions in a 3D environment. Our model, MiniGPT-3D, has been trained through a meticulous 4-stage process. In the second stage, we transferred the vision language knowledge domain to 3D space, establishing the 3D language knowledge domain. This was achieved by fine-tuning 4 key components: the point cloud projection layer, the Q-former, the modality projector, and the LLM. In the third stage, we further fine-tuned the modules and utilized a more challenging dataset to enhance MiniGPT-3D's 3D language knowledge. This process allowed our model to gain a deeper understanding of 3D point clouds and gradually transfer the powerful priors to be the 3D language knowledge. These stages of training have led to the impressive results you see in the figure. The model's ability to comprehend and respond to complex instructions in a 3D environment is a testament to the effectiveness of our training strategy. Begin at frame title at the power of MiniGPT-3D. Begin itemize. Performance and efficiency. Begin itemize. Outperforms SHAPE-LLM 13B with a 6.77% increase in classification accuracy and an 8.12 increase in GPT-4 evaluation score. Achieves this with significantly fewer resources, requiring only a single RTX 3090 GPU and 26.8 hours of training. Itemize. The mixture of query experts, MQE. Begin itemize. A unique feature of MiniGPT-3D, enabling adaptive aggregation of features from multiple experts. Uses only 0.4M parameters, dynamically adjusting the cooperation between experts. Itemize. Future prospects. Begin itemize. MiniGPT-3D is a pioneering step in efficient 3D LLM. Aims to inspire new insights and advancements in the field. Itemize. Frame. Moving on to our conclusions and remarks, we've seen how the mixture of query experts, or MQE, plays a crucial role in our model. This innovative approach aggregates multiple features from different experts, providing a more comprehensive understanding of 3D data. Despite its complexity, MQE is surprisingly efficient, requiring only 0.4M parameters. Moreover, it dynamically adjusts the cooperation relationship between experts, ensuring optimal performance. Most importantly, MQE aggregates 3D features from multiple perspectives into the semantic space of 2D LLM. This allows us to leverage the power of 2D language models while still capturing the richness of 3D data. In essence, MQE is a bridge that connects the 3D and 2D worlds, enabling us to extract more meaningful and actionable insights from our data. Thank you. In conclusion, one of the key takeaways from our research is the remarkable resource efficiency of our training process. We've managed to significantly reduce the amount of training resources and trainable parameters required. This has led to an acceleration of up to 6 times in our training process. Furthermore, we've achieved a reduction of up to 260 times in trainable parameters. This efficiency is not only beneficial in terms of time and resources, but it also opens up new possibilities for further research and development in the field of 3D language knowledge. Thank you for your attention, and I look forward to any questions you may have. In conclusion, our work has made significant strides in the comprehension of point clouds. We've demonstrated that our model has an excellent understanding of these 3D data representations. This is largely due to our innovative approach of leveraging the powerful priors from 2D language models, or 2D LLMs, to build our 3D LLMs. This method not only enhances the model's comprehension of 3D geometry, but also makes the alignment process extremely efficient. Moreover, our model supports multi-turn dialogues with users regarding the input 3D point cloud. This interactive feature allows for a more dynamic and engaging user experience. In essence, our work bridges the gap between 2D and 3D language models, opening up new possibilities for future research in this field. Thank you for your attention, and I look forward to any questions you may have.